Greetings, my name is Emory University. I'm a member of a team at Emory University and the CDC, which has been producing a novel genotyping and mathematical algorithm for estimating the multiplicity of infection, or MOI, of malaria parasites. And I want to show you this cocktail of math and public health that we have produced. First observation. If we can look at this graph over here, you'll see that despite interventions, there was an initial drop in Western Kenya of malaria prevalence, but it has now plateaued in the 2010s. So what's going on? Second observation is that if we use heterozygosity to, as assessed by microsatellite repeats, as a surrogate for malaria transmission intensity, what you'll see is that there's very little change over time. And this is in spite of initial change in the malaria infection prevalence. What you also see is that the heterozygosity has not decreased. It's just stayed the same, which is something you would expect if the parasite population size would actually have decreased. So given these two observations, there's something more to malaria intensity. So based on the information, we're not really sure what's going on. We don't know how all these different intervention programs are affecting the parasite population and the malaria transmission intensity. So the particular question we have here today is, can we use better molecular tools than microsatellites that we have, and a better analytical approach to try to estimate the changes in transmission intensity after these malaria interventions that we made? So can we see more what's happening in these areas, and particularly in high transmission areas? So our goal is to study 24 SNP barcode sequences that were identified by Harvard and try to quantify the multiplicity of infection as a surrogate marker for the intensity of transmission. But even if we succeed at doing that, we have this analytic challenge. We're missing the analytic tools to be able to estimate the true malaria prevalence. We don't know how to assess multiple different clone infections. So the laboratory method that we use is modification of the standard Harvard procedure, except that we have 3 multiplex PCRs of the PCR locations, followed by deep sequencing of all amplicons and bioinformatic processing, where we are going to need a new analytical approach. So I'm going to focus on that here today. So the analytical question is really, in the drop of blood, can we find the most likely identity and the most likely number of P. falciparum malaria clones in that drop? We did a pilot where we mixed together 2 known isolates. We spiked laboratory isolates consisting of whole blood and cultured ring stage parasites with known SNP barcodes. And for validation, we also used 3 or 4 cloned mixtures. And what we found is that the amplicon ratio was preserved across the different locales, even when we had the background of DNA from frozen blood samples and dried blood spots to simulate the real field conditions. So what we can imagine now is that, here are the different numbers, each of these sites can be referenced as either a 0 or 1, whether or not it follows the reference genome or not. So instead of all these G's and A's, we can just say, this is the reference genome, this is a deviation from a reference genome. So now we can actually formalize the problem. So suppose that we look at what's known and what's unknown. Suppose the known quantity here is the SNP measurement from the multiplex PCR. And here are the different measurements for the 24 different sites. Suppose this is the vector D, and that it is known. Let's further assume that we also know how many clones there really were in the data. And let's call that number K, number of clones K. Okay, we're going to remove this assumption in a little bit. And just to illustrate, if we further assume that we know what these clones are, suppose the first clone is this deviation from the reference genome, so 0s and 1s, and the second one is this one here, and here's the third one. We know that there are 3, and these are the barcodes that correspond to them. But what we don't know is the mixture of them, the proportions in the actual mixture. Now we're going to call these different barcodes a matrix M, or barcodes matrix, and we can assume that that's known as well. And then this particular problem here is saying, hey, what are the proportions so that this M times W is the vector D? And this yellow thing that I'm pointing at here is the reason for these particular sets of equations. We can say that, like, well, it's really like we're taking, at this particular site here, we can ignore the 0, and we have the value of W2 and the added value of W3, and that adds up to being 0.94, which is just a linear equation. It would be really nice if this was the whole story, but of course, that's not the whole story, because we have error in measurements, and we have noise, and various things. In particular, at this other side over here, at SNP side number 6, we have the number 0.92, which is also the addition of W2 and W3. So obviously we could need to do a little bit better. The way we formalize is to say, well, let's not make it an exact equation. Let's make it a minimization problem. Say, let's minimize the difference in noise between n times W, which is what we predict is true proportions times the strains themselves, minus what we actually measure. Now, this problem is something that we can actually solve, but let's make it slightly harder. The way we solve it is just using Tikhonov regularization. But we can actually solve a hard problem here, which is when we take away the assumption that we actually know the clones and what they are. If we don't know that, then the question really becomes, hey, can you find us a matrix M and the vector W so that we minimize this quantity called the misfit? Now, if we can do that, we could do a lot. This particular problem is outside the realm of regular linear algebra, and so we're going to need some new tools. This is something called an inverse problem. In general, this is an inverse problem. If we take a Bayesian approach to it, what we're saying is that, well, the probability that we'll see vector D, given that we actually know the barcode matrix M and we know the proportions W, then assumption we can make is to say, well, let's say that the noise itself is Gaussian and that it's independent. We can encode that with something called capital gamma. If that is true, then we can use the Bayes theorem to take this likelihood, this prior here, the likelihood of measurement, if we knew both M and W, and turn it around using Bayes' rule and assess the posterior distribution, which is what we're really interested in, which is what's the probability that we'll see both M and W, given that we see the measurements D in the field. And that's this expression over here, which also encodes two things for sparsity, another prior, as well as something that minimizes the size of the solution. Now, we have solved this problem, and the tools we came up with is an algorithm that maximizes this posterior distribution, called a map estimate, a maximum a posteriori, which takes this enormous search space and is able to go through it in time that's linear in the number of SNP sites and exponential in the number of strings. And we're assuming that the number of strings is actually small, so that's actually pretty good. We also have an algorithm that measures the uncertainty we have in the estimation. So we could have multiple solutions piled on top of each other. We can measure this uncertainty using Markov-Chain Monte Carlo, or Gibbs sample. Now, at the bottom here, I've just made the problem a little bit harder. What if we actually don't know the number of strains even? Well, then we can repeat this algorithm just for different values of k and measure the decrease in misfit. And once that misfit hits a me, we know that we actually hit the correct number of clones. So if we look at the problem right now, we're actually in a state where we only are given the measurements and we can estimate everything else. And that's the novelty of the approach that we have here. Now, based on this, we ran a pilot, and in our pilot, we found the most likely number of clones 80% of the time. And this includes really low concentrations of code, like 0.5 to 2% concentrations. We went further and tried to find the identity within those examples where we found the right number of clones, and we were able to find the primary one almost 100% of the time. These are primers that existed in at least 80% proportion. And we found the secondary one, which existed in 2 to 10% proportions, 85% of the time. And then even 80% of the time, we were able to find the tertiary one, the really small ones. And we went further and found the quaternary ones in the cases where we actually had 4 strains, which happened sometimes because of mutation. Now, we also tested this in the field. So we looked at the Western Kenya data from 1996 to 2012, which are SMEW positive samples from 4 population surveys in Asembo, Kenya, starting in 96 and going through interventions in 2012. And what we found using this method, if we just measure the number of strains, that there's a marked decrease, especially between 2007 and 2012, which is significant, where we see that the number of strains that we're measuring in the lab data is going down. The number of people with 1 strain or 2 strains is now significantly greater between years than the ones with 3 and 4 strains. We're looking at proportions here. And if we chart the identity of these strains, what we'll see is that these are the communities that we detected from the strains, is that they have a lot of structure. So if you look at the structure here, you'll see that the communities themselves exist, and there's actually quite a bit of modularity here that's missing. You can see the years now. So the conclusion is that we actually have a method that gives us better accurate information relative to other approaches. which means that we can actually use this modified 24-SNP barcode assays and our algorithms to actually get better information into what's going on. We can measure change in intensity over time by using this Western Kenya study. And what we also find is that there's a change in transmission intensity without actually a change in the prevalence of infection. This gives a number of applications. So we can have a better measure of the transmission intensity, the length of infection within the hosts. We can assess how well your intervention impact is, even if you have high prevalence. We can even measure the clone distribution within the population instead of looking at individuals with single clone infections representing truth. And this generalizes to other scenarios. For instance, when you have a large number of similar clones or other kind of bacteria with a large DNA background in the background, for instance, E. coli and feces. If you have any questions about this particular approach, please don't hesitate to contact us. Thank you very much.